do this?
Yes, sure. This, where does it go? Oh, right. Okay. Info theory, yeah, perfect. The first ones, yeah. The first, yeah, and the second one is the next talk after.
This one.
Okay.
Where it doesn't bother you.
Yeah, this one is good actually. Ah, it goes the other way.
Strange, right?
Very strange. Very strange. Up is down, down is up.
Yeah.
So this is.
It's on.
It's on. Okay.
Yeah, it's on because otherwise here is mute.
I see. Okay. Okay.
But I would prefer
Oh yeah.
if it doesn't bother you.
That's okay. Yeah. And this works. Ah, perfect.
Okay.
Yes, thank you. Thanks. So.
Fellowship, and today he's going to tell us about clocks and synchronization, for which he'll get the minutes that we've missed due to our poor synchronization.
All right. Thanks, Elena. Really great to be here. See so many familiar faces, also new ones. Yes, so this is work that's completed but still to be put online, hopefully within the next 3 weeks. And yeah, it's an information theoretic look at clocks and synchronization. It was done with a lot of people, primarily Leonard Baumgärtner, who's unfortunately no longer in academia, but he was doing his master's thesis on this as well as other topics. Gilles Putz, Henrik Wilming, Yuxiang Yang, who were all at ETH while this was going on, although none of them are at the moment, and Renato, who's the head of the QIT group at ETH. Okay, so what is the motivation for an information theoretic look at clocks? And really had two separate fields that we were coming from that indicated this might be useful. And one is really looking at the notion of reference frames, which is something that interests people here in Vienna as well. Because a reference frame, at least in the viewpoint of people who are doing relativity and Einstein, you just had a grid of clocks and rods, essentially. This was your reference frame for space-time. And this is how the GPS also works the same. You have clocks in different positions, they send you signals, and this is how you really zero down on your position. And so what we wanted to do is to really make an information theoretic look at what an observer sees when they have a system of clocks around them. So one example would be, this is somehow a space-time diagram, and you have these two black lines, which are the world lines of two agents that are going through space and time. So I guess X and T on axis that you choose, X and Y here would be X and T. And you have two clocks. Also, they have their own whirl lines, and they send out signals. So assuming the clocks send out photons as signals that a unit of time has passed, you get these 45-degree angles. And each of the agents, what they receive really is a sequence of ticks. We call this fundamental signal that a clock has said a unit of time has passed. We call it a tick. And they get a sequence of ticks from these two clocks. And that essentially is their reference frame for time. All of the other events that happen, they can order them with respect to when they happened within this sequence of ticks. The other entirely independent motivation for this is really the operational timekeeping. We've had a lot of people here in Vienna as well have studied the accuracy and precision of clocks from various viewpoints, either from the resources being thermal engines and entropy and heat, or the resources being the size of your quantum Hilbert space. And we wanted to really unify all of the different ways in which we look at the accuracy of clocks, because so far you can talk about Allen variance. This is what people use in atomic clocks. You can talk about signal to noise ratios. You can talk about synchronization games. But each one of them is very specific to a particular scenario. And if you change the scenario, they don't apply as well. And usually the advantage of looking at information theoretic analyses of stuff is that it becomes much more general. It sort of goes out of the specific scenario that you're talking about and gives you a sort of a viewpoint that applies more generally. OK, so now I want to clarify what exactly I mean by clocks. So in this work, we really talk about clocks as autonomous emitters, not triggered devices. So a classic example of this would be, imagine you have a race that someone is running, and you can have two different types of tasks. You can have somebody ask, well, how long did the runner take from the start to the finish line? And for that, you don't need a clock that's an autonomous emitter. You need a stopwatch, something where when the runner begins, it triggers a preparation of a state, and when the runner ends, it triggers a measurement of the state, and you make a time interval measurement. But the other task you can imagine is that there's a photographer at the site of the race who wants to take a picture of how the race looks every 1 second. And so they cannot wait for someone else to tell them when to take the picture. They need an internal device that tells them 1 second has passed. And that's really the type of devices we're talking about. We call these ticking clocks. And so they differ in the sense that their fundamental output is really telling you how many units of time have passed. So that's the output of a ticking clock. Whereas stopwatches, their fundamental output really is the result of a measurement which tells you delta t, a time interval. OK, yes, and as I said, the motivation for this is that this becomes now dynamics independent. So we separate the information theory from really the physics, well, not necessarily always, but at least a little bit of division between just the information side and what specific system we're using for a clock, whether it's atomic clocks or heat engines or anything. And of course, the eventual goal would be to use these general results to link to dynamics. And okay, I recycle these slides from a previous conference in which I was predated by another talk that actually used information theory to link the precision of clocks to the dimension of the Hilbert space the clock works in. So that's why this is sort of an example. That paper by Yuxiang Yang and Renato Renner is an example of such an approach. And also more generally, for a theory of time, we would like to have a construction that is independent of the manner in which the dynamics has actually led to the signals that you see. So when I talk about the tick sequences, of course, we can link this to quantum theory. But in principle, if somebody was looking for some generalization of quantum theory or something that would maybe link to gravity or a future theory, you could in principle still use this information theory, because at the level of the observer, the only thing you care about is the sequences of signals you see from the clocks. All right. So now I go into the actual theory. May I come this way for a change? Yes, this is more comfortable. OK, so the fundamental object on which we base the information theory is really this random process of ticks that we receive. So you have the clocks, they send you ticks, and this is really a random process, like what exactly you observe. And so an observer, essentially, you can write what they receive from each clock as, or what they receive is basically a message. And A and B here are the two clocks that are present. And the lower index just refers to the index of the message that you receive from the clock. But this you can split into two parts. One is just the ordering between the messages. So first you received a message from A, then from B, then from B, then from A, so on and so forth. And the other part is what the message is actually. And we really are focusing on the top part, because the bottom part is really the standard information theory of Shannon, this how to deal with encoding of messages. What we really want to look is at the information encoded in really the synchronization of the messages with respect to each other. So a general object is really the possibly infinite sequences of ticks that we receive. So I use this x bar to denote a sequence, and each xi is really a label that's picked from the set of clocks that we have. And from here we can split into two cases. One of the cases is the infinite case. We look at infinite sequences and we look at the asymptotic properties of this sequence. So for example, is it stationary in a certain sense? Do you, after a long time period, have certain properties that you are guaranteed that will hold true, such as the average frequency or average entropy rate? This is usually, in the infinite case, the most important thing that you look at are the entropy rates of production of this random process. But you do not necessarily have to look at the infinite case. You can also look at the finite case by defining what is called a stopping time. And it's essentially a condition at which you truncate the sequence. So you can consider, for example, the easiest example is the alternate ticks game, which is one in which you truncate the sequence the instant you see two ticks from one of a pair of clocks before the other one ticks. So you continue as long as you receive the ticks alternately from either clock, and the instant that fails, you truncate it. So these lines here show where it's truncated, and these only the branches ABA and BAB are the ones that continue, so on. And just out of interest, when you do such a thing, the set of sequences that you get, it forms a prefix code for the whole tree of tick sequences. Okay, so one can show that once you define such a stopping time, which we assume to be deterministic, so it's not a stopping time where you go, well, if I see this condition, there's a probability of stopping. It's really a fixed, either you see a condition and stop, or you don't and you continue. Then you get disjoint sequences. You can define probability distributions on these. In the language of probability theory, these are so-called cylinder sets on the set of infinite sequences. And so yeah, you see you can have a sequence AA, ABB, ABA. These are all sequences that have been truncated by the stopping time of the alternate ticks game. But you cannot have both ABB as well as ABBA. You cannot have a sequence that is a subset of another one. So the prefix of another one. So okay, so we define the probability distribution over these things, and so far so good. Some examples for relevant scenarios. If we wanted to look, for example, at how long it takes for one clock to tick with respect to the other. So this is really looking at one is your reference clock and the other is your clock of interest. Then your stopping time would be really the instant I see the first tick of the clock of interest, I stop. And so your set of tick sequences are all of the form, I see n ticks of my reference, and then I see the first tick of B. Another thing you can look at is Allen variance. So in the Allen variance, you have a reference clock, and then you look at your clock of interest, you look at how frequent it is with respect to the reference clock. So here you would look at how many, so A is here your clock of interest, and you intersperse n1 ticks of A, n2 ticks of A, nm ticks of A, in between which you see a tick of your reference clock. So the deviation in n is really where your Allen variance is calculated. And as I said, the alternate ticks game, you truncate it when you see consecutive ticks. So these are the four possibilities. You tick alternately for n times, and then you have one of the four possibilities of sort of failing the game. Okay, so this is all well and good. We defined a sort of a probability theory, but now we really want to define an information measure on this set. And the manner in which we did it was sort of resource theoretic. So the first thing that we did was to define what would be the free distributions. What would be a set of clocks which are not synchronized at all. So there's no information that you expect to have. And so this is analogous somehow in the normal Shannon entropy case. You have the uniform distribution is your free distribution. In the case of thermodynamics, you have the Gibbs state, the thermal state, which is the free distribution. And in both those cases, you can define a very useful information measure as the relative entropy to the set of free distributions. So in the case of, well, up to an additive constant. So in the case of Shannon entropy, it's just the normal entropy is also the relative entropy to the uniform distribution up to log D. And in the case of thermodynamics, free energy is a relative entropy to the thermal state up to log of the partition function. So we do the same thing here. And the information in synchronization really is the dependence of your next tick on your history of the sequence. So this is the thing that we want to say, well, if you have a free distribution, there should be no dependence on the history. And that is what that has a well-known name. It's called the Bernoulli distribution. This is a random process in which the probability of seeing the next tick from any one of the set of clocks is a number that is independent and identical. It's an IID distribution, so it's one number independent of the history and independent of where in the sequence you are. You can also derive the Bernoulli distributions axiomatically by the two axioms that the past cannot predict the future of the tick sequence, and also the present, the tick that you see cannot predict where in the sequence you are. Although this, of course, requires you to start from a prior, and then the exact statement is that if you have a prior distribution, observing a tick does not give you any more information via Bayesian update. Okay, so the Bernoulli distributions, they have some very nice properties. So if I take a Bernoulli distribution, it's defined really as a generating thing, like I generate the tick sequence in an IID manner. But if you then define a stopping time, and you look at the relative occurrence over the entire probability distribution of which clock ticked. So if I have two clocks and I see that they were generated by a Bernoulli distribution, and on average I saw an equal number of ticks of A and B, then it will turn out that that is exactly the same as the generating probabilities. The Bernoulli distributions, the global average is equal to the generating the probabilities themselves. So this is the equation I've written. The average number of the ticks that you see from one clock divided by the entire thing, so that's the relative occurrence, is also equal to the generating probability that really goes in order when the sequence is generated. Okay, and because of that, the probability of seeing a particular tick sequence you can write very simply as just the product of that frequency raised to the power of how many ticks you see. So if I have a sequence of 5 ticks and 3 times A and 2 times B, then it's just going to be the frequency of seeing A to the power 3, the frequency of seeing B to the power 2, and that's it. And so our central ansatz was, well, let's define now, as I said on the last slide, a particular information measure to be just the relative entropy of my real probability distribution from the clocks that actually exist to a Bernoulli distribution. And then I minimize over all Bernoulli distributions, because remember, I have the Bernoulli distribution is set by this parameter. So if I have two clocks A and B, I have in principle a family of Bernoulli distributions where I have to choose the relative frequency between A and B. And so what you do is you say, okay, that's the set of free states, and the minimum distance to that set is really my information measure. It actually turns out that this minimization is quite simple. What it does is it gives you the Bernoulli distribution with exactly the same average relative occurrences as your real distribution. So if I had a real distribution that had 2/3 chance of A and 1/3 chance of B, the closest Bernoulli is going to have exactly the same generating probabilities. Which is also nice because this can be interpreted as a coding inefficiency. So if I define a game as follows, somebody knows both me as well as all of you know the average occurrences of A and B in this scenario, but not the exact probability distribution. And then I receive the actual tick sequences, I observe them, and I have to communicate that to you. The number of bits that I have to communicate on average is exactly this relative entropy. This is just a property of the relative entropy of the Kuhl-Black-Leibler divergence. Okay, right, so this is a little bit of math, but it's just to say that because the information measure is a relative entropy, and because the Bernoulli distributions have this nice form, they're the probabilities exponentiated by the number of ticks you see, the logarithm, all of that sort of simplifies, and at the end what we get is a very simple result, that the information measure is really the negative of the entropy of the probability distribution. So this is just the Shannon entropy of the probability distribution. I saw this sequence with this property, that sequence with another property, etc. Plus the average number of ticks times this, the entropy of just the set of probabilities, the average occurrences. So an example, if I have a probability distribution where A and B are equal, then this is just going to turn to log 2 because this is going to be the entropy of the distribution half comma half times the average number of ticks I see in total, and then subtracted with my entropy of the probability distribution. And so one of the things we can see immediately is if we have that tau goes to infinity, the average number of ticks goes to infinity, which is what we would do if we were looking at the asymptotic properties, and you divide by tau, then you really get that the limit of this entropy rate is the entropy of the Bernoulli distribution that matches it. So limit of I is that entropy minus the entropy rate of just the probability distribution, for example. Okay, And this has some nice properties that you would expect. It obeys a lot of data processing laws. So for instance, if you start with a stopping time tau and then you reduce it to tau prime, so you have another stopping time that always ends at the same time as tau or stops before that, then as you can expect, you lose information. So your I prime is going to be less than I. If you have a set of, let's say I have a set of 4 clocks A, B, C, and D, I have that property distribution. I can always then separate it and create the marginals on A and B and C and D alone. And as expected, the full information measure is greater or equal to the information measure when I sum up all the marginals. And the last thing is it allows for extension. So I can take any tick sequence with some stopping time, and then I can extend the stopping time and not increase the information measure by just making the extensions Bernoulli. So they are by definition 0. And then via doing this, I can also take a probability distribution just on, let's say, A, B, and C, D, extend them Bernoulli as I like, and then bring them together with them being relatively Bernoulli as well, so that there's no information in the synchronization between one set and the other. And then you can end up with the information measure being exactly additive, because in principle it's super additive, but you can define sort of a tensor product the way you do it in quantum mechanics as well. And of course, this information measure 0 if and only if you actually have a Bernoulli sequence. Okay, so one of the goals of getting an information measure is really, as I said, to make it more general than the other ones. And the way we see this is we see that the information measure ends up upper bounding everything else that you can think about measuring. So for example, you can define a synchronization game. The alternate ticks is one version. And you can look at usual measures are how long on average before you fail the game. Or you could do a one-shot thing where you can say, what is the probability when I do this game that I succeed up to n? And in both cases, you can bound it from the information measure. So for example, we know, I wrote down this formula previously, that the information measure is given by the average number times this entropy minus the entropy of your probability distribution. And you can use the fact that the entropy of any probability distribution is positive to get one bound. But you can also do the opposite direction, because this is not actually unconstrained. If you fix the average number of ticks you see, then it turns out that this entropy has a maximum value. The easiest way I have of understanding this is that you can cast this into the form of a free energy, essentially, where you take the number of ticks you get and you consider that to be an energy level of a Hamiltonian, and then this becomes proportional to the energy, and now you have the energy minus the entropy, so it looks like a free energy. And we know that for any fixed energy, there is a maximum entropy. That's the property of a thermal state. It maximizes the entropy given a free energy. So all of this is just to say that you can also bound it the other way. For a fixed tau, you can upper bound h, which ends up bounding I, and yeah, you get this. It's just a Lagrangian optimization, and that gives you an upper bound on. So this is a plot of the information measure and the average number of ticks we see in the alternate ticks game based on that. It's not the reason I draw a plot and a region plot is because there is no closed form. You have exponentials mixed with linear terms, so you have to do a parameterized plot, for example. And so for the alternate ticks game, as an example, you have this formula that the total number of alternate ticks game is less, the alternate ticks before you fail is less than 3 plus I plus square root of 2I log 2 Sn. So essentially linear in I for large enough I. Yeah. You can do the same for the success probability. You say, what is my stopping time now is actually, I do it in 2 steps. So I take the alternate ticks game, I say, well, let my stopping time be just wait till n ticks. So this is one simple stopping time. I stop after 10 ticks. But then for the purpose of the alternate ticks game, I can take another stopping time, which is the minimum of either I stop after n ticks, or I can stop before if I fail. So this way I either get to fail or I stop at n ticks either way. And we know from data processing that I in one case is less than the other. And the I of so I of tau star is less than I of tau. And I of tau itself, stopping at n ticks, we write it as the sum of the cases in which I succeeded to n ticks plus the sum in which I failed to n ticks. And then again here it's just a Lagrangian optimization to see what's the probability that maximizes one versus the other. The details are not so important, but what you get out at the end is that the optimal version is where the information measure is the binary entropy, binary relative entropy between S, which is the actual probability of success that you've asked for, and R, which is the best probability of success you could get from a Bernoulli sequence. So I could say, I want to succeed until n ticks. so 100 ticks, say, for example, and I look at all of the Bernoulli sequences. I see what the best probability of getting to 100 ticks is, and then I look at that with respect to my actual probability, and I is lower bounded by that amount. So in this case here, you can also do a similar thing. For every information that you are allowed, you can upper bound the success probability that you have. So if I wanted to succeed to 5 ticks of the alternate ticks game, it turns out I need 4 bits of information, for example. If I wanted to succeed only to 3 ticks, I need only 2 bits of information, etc. So you can do such things. Right, and then the final thing is, so until now everything that I've spoken about is very discrete, so I have discrete tick sequences. But when we have quantum theory, sometimes we look at continuous signals. So typical example is in the papers that the group in Vienna have on thermal clocks is you look at this waiting time distribution. So you have a clock with respect to background Schrodinger time, and all you observe is the amount of time it takes before you see, say, one of the ticks. And you want to then talk about we want to talk about the information that is encoded in this waiting time as well. Because so far, the usual ways of looking at it is via confidence intervals and precision, etc., which I will speak about in the next slide. But this discrete scenario can also be turned into the continuous scenario. As I said, if you want to look at a single tick of a clock of interest, you just define a reference clock, which I call C, and then you ask, well, how many ticks of C do I need before I see the first tick of A? And so this is just n ticks of C and then 1 tick of A. So you end up with a probability distribution over n, essentially. And as the frequency of this reference clock goes to infinity, I end up with, well, this can be turned into an integral form, and I end up with essentially something that looks at the integral of the waiting time distribution. So when we take this information measure and we take that limit of the frequency of our reference going to infinity, we end up with the information measure being related to the differential entropy. And actually the formula on the right is the more physically instructive one. It's the relative differential entropy to Q of t, and Q of t is essentially a simple exponential decay. And the reason that we get this is a simple exponential decay is really the continuous version of Bernoulli distributions. So Bernoulli distributions are the free distributions, IID sequences when you have discrete stuff. And a simple exponential decay is the continuous signal version of something that does not depend on history. It's the probability of generating an event is exactly the same number independent of what has happened before. And just like in the discrete case, the particular one that minimizes the relative differential entropy is the one that has the same average as the actual waiting time distribution that you have. Okay, so I mean you can also write it in this form where mu is the average of omega, but the important thing is it is this relative differential entropy, and it's also scale invariant. So if you scale the waiting time, it doesn't matter. It's really its properties with reference to itself that are actually more important, not with respect to another clock. Okay, and so as in the discrete case, you can use the information measure to bound other measures. So one typical thing that people look at is this ratio R, sometimes called A or N, depending on which paper you read. But it's a ratio between the mean squared of the waiting time divided by the variance of the waiting time. And the reason this ratio is nice is because if you ask the question, on average, how many events do I have to wait for before the uncertainty in the next event is actually of the order of the time between events. So for a watch on the hand, for example, would be how long before my watch is off by 1 second. Then the average number is exactly this ratio. So that's why it's a nice thing to look at. Unfortunately, because it depends on the variance, it can be pathological because you can make a little bit of a tail for a distribution that completely screws up with this ratio. So for instance, if I have a clock that almost always ticks at t is equal to 1, but there's a small epsilon probability of it ticking at 1 over epsilon squared in the future, then what you see is if I take epsilon going to 0, this turns in the limit to a perfect clock because it just turns into a delta function here. But R tends to 0 just because this tail is so far away to the right asymptotically. So it's not a really good measure for pathological cases. But we see that I goes to infinity, as it would be. Any delta function, the differential entropy is going to explode. So I goes to infinity, which you would expect from a perfect clock. In the more general case, you can do an optimization of I versus R. And you get this expression that I is always greater or equal to something that scales with log of R. It's not exact equality because the way you get this is by looking at Gaussians. which are exactly those functions that minimize the variance versus the differential entropy or maximize. I'm not sure which order, but Gaussians are the ones that satisfy this.
Maximize the variance, the entropy for a fixed variance.
Thanks. So they maximize the entropy for a fixed variance. Thanks. And that gives you this bound. But Gaussians are defined on the entire real line, whereas waiting time distributions are only from 0 to infinity, which is why it's not tight. But as I and R both increase, it becomes more and more tight because the Gaussians that are further and further to the right, their tails in negative t become smaller and smaller, so these two become closer to each other. And yeah, if we link to this other paper that I mentioned that linked R to the dimension of a quantum clock, so there they prove that the R value for a quantum clock of Hilbert space dimension d is upper bound by something that scales with d squared. Then using this formula, you see that I would then scale as log d, which is kind of neat because this is what you would expect if you have d-dimensional Hilbert space. You can do the same for confidence intervals. So you say, well, imagine that I have a clock that I know must stick within t, that's a delta interval around t is equal to 1, and also must stick with a probability 1 minus delta. This is, I'm just constrained it to give it an example. Then you see that this delta scales as the exponent of 1 minus I. So as I goes to infinity, delta can go to 0, and you get a sharper and sharper clock. Right. And how much time do I have? Oh, excellent. Yeah, half an hour. I'll be finished before time. Yes. So the final thing to say is that another way of looking at all of these quantum clocks is really as what we call a hidden Markov model. And to those who are not familiar with this terminology, what a hidden Markov model is the composition of two things. You have an underlying Markov process, so it's just let's say a chain of states which may be classical or quantum that you can sort of move through. And on top of that, you have on an upper layer, you have some sort of measurement process that gives you an output depending on where you are within the state space. So for example, a typical way of making a clock is to have it to have some state space where the clock is sort of moving through, and you decide whether the clock ticks or not by measuring whether it's at a particular level within the state space. So this is why we would call it a hidden Markov model. And the nice thing about this is if you have a quantum clocks, let's say A and B, two of them, and I have the dynamics for a small time delta t. So in this slide, I'm considering I have a background Schrodinger time and quantum theory. Then I have sort of three things that can happen at any particular time delta t. I can either have that neither of the clocks tells me that there is a tick. I can have that clock A tells me that there's a tick, and I can have that clock B tells me there's a tick. As the limit delta t goes to 0, we ensure that there cannot be simultaneous ticks, although it's not a problem to generalize this theory to include simultaneous ticks. Okay, and yeah, if you do this, you can essentially create what we call an effective map. So in this picture here, you really see in delta t which clock is going to tick or not. But what we would like to construct is a map that tells us, well, I want to know which is the next clock to tick, and if I see the next clock to tick is A or B, then what is the state of how does the quantum state change in between? And you can do this. You simply sum over all of the ways in which you cannot see a tick until you see the first tick either from A or B, and that gives you an effective map. And the reason for all of this is to say, well, we could also consider from the viewpoint of reference frames, we can consider this to be a starting point for the whole point of reference frame. So we can say, actually, I don't have Schrodinger time, but all I have is an effective map that tells me which clock is the next one that the observer is going to see, and this is now their reference frame. So then I upgrade something that I derived from quantum theory to sort of the level of maybe independent of quantum theory, this is actually what a reference frame should look like. So yeah, so this is all to say that clocks are really an example of hidden Markov chains, and as such, they can be used to study reference frame in a more general manner. Specifically, the usefulness of this is that you can use this on any finite clock, and this gives you things that, in the limit that the clocks are perfect, will turn into things that look like the Page-Wouters formalism, and when you have perfect continuous clocks in the background. But if you still have, not in that case, you can still create reference frames with imperfect clocks and consider what happens. Yes, and this allows us to calculate then entropy rates for quantum and classical clocks, because once you have the effective map, then you can write down the stationary properties of random processes. I wouldn't go into detail now, but for those who are familiar, this allows you to calculate entropy rates, and they scale as we would expect If you have quantum clocks that generate these maps, then we get an entropy rate of log d. But if you have classical clocks that, classical dynamics that generate these maps, you get an entropy rate that scales as half log d. So it's less than the quantum case. Yeah, so there's lots of open questions and further work from this. On the information theory side, we can consider indeterminate stopping times. As I said, I consider deterministic ones. We can consider drifting frequencies. So everything I spoke about, we really made the free distributions, the Bernoulli sequences, IID. And in principle, you could consider that clocks remain very well synchronized, even though their frequencies with respect to each other are allowed to change. But they're allowed to change in a very sort of well-ordered manner. So for that, you would have to create a new set of free distributions and generalize the information theory. We also have to consider more information measures because just like in the case of thermodynamics and cryptography, the normal entropy is a nice starting point, but depending on the scenario, you require Renyi entropies or one-shot entropies, min-max entropies, etc. And you can easily construct similar examples here as to why the information measure I talked about does not capture every scenario perfectly. And of course, entropic rates, as I said. And on the dynamical side, a big thing is to link this to physical variables. Most top of the list for me is the Hilbert space dimension, because it's a very information theoretic question, and entropy, because this is very much in the direction of like what is a thermodynamically autonomous clock, the optimal thermodynamically autonomous clock, how much entropy or heat must it dissipate or generate or consume in order to create a certain amount of precision. Yeah, and then to really study the bounds of all of these for the quantum case, for the classical case, and if people have more general ideas of physical theories, what happens in that case as well. Yeah, and reference frames, of which I've also already mentioned in passing in many slides. That would be all. Thank you. Any have questions or comments? Yes.
Just one question because of what we were talking before about kind of algorithmic things. So information theory and information measures can also be, in many cases, translated to the notion of Kolmogorov complexity.
Aha.
And there, what would happen here? Because so here you look at the relative entropy, to this Bernoulli minimizer or Bernoulli
Yes.
distribution, and in the Kolmogorov setting, I have no idea what the function would be. But
Yes. So off the top of my head, I don't know, but I think the Bernoulli sequences are sort of the minimum complexity in the sense that the only thing you need to generate the sequence is just this set of numbers.
yes, to
But
generate them, but they
yeah.
are completely random. Now, if you look at the concrete example of such a sequence, the program that
Mhm.
gives you this sequence will be